First of all, welcome everyone to this multiplayer Pac-Man with RSocket session, and thank you a lot for choosing my track. It's really important for me to see that a lot of people who want to learn something new about reactive programming, especially about technology on which I'm working on today. This is RSocket. And today, as usual, I want to preserve your time. I want to let you know as much as possible and take from this conference as much as possible. So I need to first of all define for whom this talk. So this talk for all people who are doing distributed system, microservices, or any kind communication over the network. Who is doing network communication today? Distributed system, microservices, all kind of networked system? I hope everyone does. If you're doing mobile client or Android to server communication, it also will work for you, so it covers almost all kind of audience today. Also, if you're curious about performance, if you want to improve your performance of your application, if you want to save money for your company, this talk for you. Because we are going to see why particular protocols are slow or fast. And finally, this talk is for all reactive adopters. So if you're planning to start learning reactive programming, if you're planning to use RxJava 2 or Project Reactor, or if you are using Project Reactor or RxJava or Reactive Spring today, this talk is also for you. By the way, how many reactive programmer adopters I have today? Just a few. Okay, that's not bad. I will explain a few basic concepts of reactive programming, don't worry, so you'll get as much as possible from this talk. All right, let's start. If you're still with me, my name is Oleh. I'm from Ukraine, from Kyiv. I work for Netify. I'm reactive geek. I love Project Reactor. I'm one of the contributors to Project Reactor. I'm one of the contributors to our Socket project, so I know almost everything about those technologies. I will be able to explain it. I've wrote a book about Reactive Spring, so you can consider me as expert in reactive programming. So, our agenda for today. Today we are going to start with problem definition. We will start looking into multiplayer RSocket and multiplayer Pac-Man game with particular different technologies. We are not going into depths about details of business logic or how to match particular players on the map, etc. But we are going to find out the fastest, the best protocol for building multiplayer Pac-Man, which should be a real-time game and high-performant subsequently. In order to figure out which protocol is the best, we have to compare them. Somehow we have to figure out what protocols do we have today. And of course, we have to have fun, because I'm expecting lots of involvement and engagement with you, so you will be able to assess every particular protocol by yourself by playing real Pac-Man online game with others. So this is your mission today, and I'm planning that you will enjoy this session by playing real multiplayer Pac-Man. And afterwards, you will be the persons who will define which protocol is the best one. All right? Does it make sense for you? Are you ready to play Pac-Man today? Great. So let's start, and let's start with problem definition or figuring out what particular multiplayer requirement do we have for our game. In order to build game accessible or available for everyone, we are going to build browser server game, because now everyone can open a browser from your phone and play absolutely without any problems in your browser. This will be the simplest way to share the gameplay with you. So, in order to build a browser server communication or game, we have to have a server first of all. And since we have a server, we have to have a browser which connect to a server and get as a response the first HTML page. Since you want to build a cutting-edge technology and cutting-edge game, you want to prepare the lightest, kind of the fastest way to send data from server to client. So we need to just send a plain empty HTML page which just link on particular scripts and data. And we expect that the server will push everything we need asynchronously. So it's kind of server-side push. Does it make sense? Yeah? So we are building kind of applications today. Once we got everything, kind of game tiles, all required information from our client, from our server to our client, we need to make the next step, which is basically first interaction between client and server. So we need to say, okay, I want to play the game. Please register me on the map. So the server will respond, for example, with a state, with the current state of the game, with all active players on the map. Then, in order to make this game more interactive, we have to share somehow the location with other players. So the simplest way to say, okay, I'm moving in this way and this is my location, is just to send on every step the location update to the server. This is the simplest solution. Not the best, but the simplest. All right, in order to get updates of other player movements, we have to listen to some stream of updates, right? So we have to connect to some endpoint and say, okay, I want to listen to updates of other players, and in this way, I will be moving other persons and characters on the map. In order to make this game more challenging, of course, we have to have a scoreboard. The scoreboard is an important part of Pac-Man. There is no Pac-Man without scoreboard, so we have to listen to score updates as well. So Pac-Man should collect food, as well as Ghost should collect Pac-Man. So this is obvious. This is what will make this game challenging and really funny for many years. All right, but so far this is just a plain client, browser, server communication. And I mentioned that there should be some distributed communication, some real microservices. So in order to make this system distributed, I decided to add a little bit of modern cutting-edge technologies like machine learning stuff, data processing pipelines, etc. So here is our application. In order to make some machine learning stuff, in order to create some artificial intelligence with some smart bots which allows us to play without other players, for example, we can make a challenge between bots or something like that, we need to collect some data. So one of the source of data would be all actions that you made on your phones. So we have to collect all the data you are doing, or all the actions you are doing on your phone, and we need to collect them somewhere. In any unclear situation, if you don't know where to send your data, just you put Kafka somewhere in between. Kafka is the proper solution. How many of you heard about Kafka before? Okay, great. That's pretty cool. Why Kafka is a proper solution here? Because we can't control the stream of data. We can't use any reactive streams technique. We can't control flow. So we know that we have to collect everything. So the clients push data as fast as possible, but since Kafka is basically an elastic storage, we can scale Kafka back and forth. We assume that this is proper solution which can handle any throughput, any stream of data without any problems. Behind the Kafka, since the Kafka is also reactive streams, we will put our data processing pipeline. So we will pull data from Kafka when we are ready to process them, because this is a real pipeline of data processing. We will process them, pre-process them how, we will try to gather them somehow, and then we will send it to final machine learning algorithm, which could work fast in case it's kind of normal state of the system. But since we are doing distributed system, we don't know at which state current machine are at that point in time, so we have to be prepared that something can go wrong and our server could work really well, as in real distributed system. So we should be ready to that, and we should handle all these cases because it's important to process all user actions in order to teach our bots. So to quickly summarize what we got from our requirements, from our communication between our client and server, we got server-side push because we need to get all the data asynchronously without additional involvement from the client. We got plain request response because we somehow have to register our client and start playing the game. We have some client-side streaming because we have to share the location updates, and we have to have server-side streaming in order to make this game real-time, right? In addition, we have machine learning pipeline, which could work slow or fast because this is distributed pipeline, this is distributed system, and we can't control the particular state of the system. We can't preserve it just work fine or say, please work fine, don't crash. So we should expect everything, and what we have to do is we have to make sure that this system works stably on any kind of, under any changes or any state of the system. So good, so far so good? Any questions? Okay, let's move forward, and let's talk a little bit about our toolkit that we are going to use in our project. So, on the backend side, we are going to use Sprint Framework. How many of you are familiar with Sprint Framework? Any Sprint Framework users? Amazing. This is the right technology. I love it. In turn, we are going to use Project Reactor because Project Reactor is a proper tool to build high-performance data and stream processing. So this is a proper solution if you want to achieve really good utilization of your system. And we are going to use protocol buffer, because protocol buffer, have you ever heard about protocol buffer before? Okay, just a few hands. So for those who haven't heard about protocol buffer is message format. It's binary message format, so it allows you to send smallest messages in the binary format without any overhead. So it's from Google, so it's a pretty cool solution, and you have to take a look at this. On the front-end side, just for your information, because we are Java developers, of course, we are using Phaser. Phaser is just a UI and game development framework in the browser. It allows us to build all these UI features and movement of Pac-Mans and ghosts. In turn, I'm using Reactor.js for the same reason, to make everything looks very pretty and understandable and for the best data processing style and speed. I'm using TypeScript because JavaScript is somewhat super dynamic language, and I prefer to make my code pretty static and clean. That's why I love TypeScript, and I'm using in my solution TypeScript. And I'm using protocol buffer for the same reason as before, in order to make everything identical on the both sides, and in order to make my message sending pretty fast. So you can find all the source code by this link. If you're curious, if you want to follow everything that I'm doing, you can find all this reactive Pac-Man and multiplayer Pac-Man source code by this link. And now we are going to quickly look at our solution. Do you see it well? Can you recognize what's going on the screen? Yeah? All right. So here I have a few modules in my system. So this is basically my game client. This is everything that I send to UI. This is basically written in TypeScript. Here I have my game server. So it's my game engine, which is basically plainest Spring Boot application. I guess everyone in this room solved the same code before or done the same code in the past. So this is a real convenient way to just create simplest Spring Boot application. And here I have plain 3-tier architecture, so this is a convenient way to build your plain microservice or a simple application, like monolith application in any cases. All right. On the other hand, I have a few parts of my distributed machine learning pipeline. Of course, it's not final. There is no Kafka here in these modules, but just assume that this is part related to machine learning stuff. All right. This is my application. It looks pretty everyday application. You can take a look at this app, and you can rerun it and rebuild the same at home. OK, let's talk a little bit about protocols. In order to start building high-performance communication, we have to figure out what kind of protocols do we have. What kind of protocols do you know today? What are you using today in order to build communication between client and server? Any idea? HTTP, yes. This is one of the way we are building communication between client and server and in distributed system in general. I heard TCP. TCP, absolutely correct way to build high-performance communication for game development, right? Absolutely correct. Do we have anything else designed for high performance? Any idea? Come on, friends, wake up a little bit. UDP, can we use UDP on the browser side? And should we consider this as reliable protocol? Unfortunately not. Maybe HTTP2? Have you ever heard about HTTP2? Yeah, everyone heard. This is also one connection, almost binary data sending, so it should be really high performant. And yeah, there is more exotic protocols so far, but we are going to focus only on those 3. But one question, can we use TCP on the browser side? Can we? Any idea? TCP between browser and server. Huh? Yes, we have to use WebSocket. Unfortunately, we can't use just a plain TCP, because TCP is not available in the browser. However, we have a more modern version of TCP, which is WebSocket, which is almost the same as TCP. So this is basically our set of protocols at which we are going to look today. Sounds good? Great. So how to compare them? From my experience, the main things that we have to consider during comparison of those protocols, there is like a few main characteristics. First one is maintainability. So what maintainability means? It means that you can Google for a particular solution and find an answer. You can go to Stack Overflow, ask how to build something with HTTP, and you will find tons of answers. This is maintainability. You can Google how to create something with HTTP, and you should find any solution, tons of examples over the Google with particularly different languages, and this is maintainability. And your code should be beautiful. This is also maintainability. So this is somewhat we have to consider because it makes your solution maintainable, simpler in development, etc. The next thing that we have to consider for our case, because we have this machine learning pipe, we have to consider stability. And every distributed system should consider stability because this is important. If you crash your system, this is what won't reflect on your business real well. So we have to make sure that our solution really work well with particular protocol. And finally, for our case, for our solution, and for any solution, and for any business who wants to preserve money, we have to consider performance. Because for our case, this should be real-time game, and our protocol should provide particular level of low latency and high throughput. Yeah, does it make sense? Great. So let's start from old HTTP. Let's just consider old HTTP, and let's take a look why HTTP is good. Why should we consider HTTP? First of all, because this is a plain and simple solution. It's supported and developed for many, many years, and everyone uses HTTP nowadays. In turn, HTTP is pretty simple in development. If you are considering this plain Spring controller, we will see there is nothing to do to just define an HTTP API, because we have all this kind of annotations in Spring, which allows us to really quickly create some simple application with good enough API definition. Yeah, right? Why not HTTP? In order to make high performance with HTTP, it would be kind of really challenging development situation. Because first of all, HTTP is it's text-based protocol. So all messages that you are sending from client to server is in text format. In turn, there is no guarantee that you will open only one connection from your client to your browser. In fact, with HTTP 1, there is high chance that you will open few more, like 2 or 3, and in this situation, your server will have to deal with one client, but with few connections from this client. And this is somewhat not good, which will impact and which will lead to slower performance. And that's why we will get higher latency. And we can nothing to do with that, unfortunately. Finally, there is communication rigidity, because from the communication perspective, because from interaction between client and server, there is only a plain request response. Even with HTTP 2, there is nothing has changed from the specification perspective, and we have only request response, and that's it. Yeah, there is some hacks like server sent event, but how many of you heard about server sent event? Just a few hands. And all of you are still using a plain request response, and this is not good. So to summarize, we have only plain communication, which is request response, which leads that our server can control stream of data in a more different fashions, and we are a little bit lack of resilience. What means lack of resilience? It means like that. With HTTP communication, our server looks like this guy under the stream from this tape. Yeah, this is how looks our communication between client and server using HTTP. And with HTTP, we have to solve all these kind of problems. We have to introduce retry logic in order to deliver something in case server drops some message or request. We have to deal with timeout because server can accept your connection, but it will be hardly busy by other actions. We have to create circuit breakers and solve tons of other problems. And we have to ask ourselves a question: do we want to solve all of these things? We can solve all of them if we just provide a proper backpressure control. But now I need to ask a question: how many of you heard about backpressure before? Okay, just a few hands. Then I need to stop a little bit at this point and explain why backpressure is really important. I need one volunteer from the audience. Please, one person who wanna throw a balls into my face, for example. Any volunteers, please? Be aware. Someone, come on, one person. There is a balls in my hand, so you have to throw them into me. Come on, one person. Yeah, come on. So we are going to play in a really simple game. Just imagine that, what's your name? Lukasz. You are client, yeah? You are in client role. I'm server. So once I start up, I'm saying to the world that I'm ready. And now the client, what client usually does, it sends messages as fast as possible, right? So your client, please send messages as fast as possible. But one point, I'm server which has only 2 hands. So this is kind of 2 threads which have to handle all kind of requests. So please start sending one by one, not all of them, but one by one quickly. One by one, all of, yeah. And yeah, that's what basically happens with, please be with me. Don't be so far. I need your help a little bit further. So this is basically what happens with our HTTP server when our client starts sending data as fast as possible and we don't have enough capacity to process all of this information. And we start drops messages, and this is not good. Does it make sense? This is an example how back pressure is the absence of back pressure. So now let's consider in the same situation, the same kind of communication, but with one additional kind of communication interaction, with one additional interaction point. Now, along with saying that I'm ready, I will say how many requests I'm ready to handle at this point in time. So it's kind of requesting of, for example, 3 element or 3 balls, because I know that I have only 2 hands. I know that I can handle only 3 or 4 balls. So please send me, I'm ready to handle kind of balls. Please send me 3 or throw into me 3 balls. One by one in the same fashion, yeah. 1, 2, and I'm ready because I know my capacity. Now I can put those balls into my pocket or put somewhere or process somehow, and now I can say, okay, I'm ready to handle another 3. 1, 2, and that's it. That's how back pressure works. Thank you, Lukasz, a lot. Now, is it clear how back pressure works and why it's important? Yeah, is it clear? Okay, great. Now we can move forward, and now you understand why back pressure is a really important part of any distributed system, because now client, along with saying I'm ready, can request some part of the data. This is about back pressure or flow control. So it's clear that HTTP1 doesn't fit our requirements, so we have to consider somewhat else. So we have WebSocket and HTTP2. Let's focus on WebSocket first, because this is really fast solution. And why WebSocket? First of all, this is the same TCP almost without no overhead. This is pretty good for us. One connection over which we can send binary data. In turn, it's designed for high performance. So we can reliably use it. Why not WebSocket? Why not pure WebSocket? If you want to build something on top of pure WebSocket, for example, using Spring or using Spring Web Flux, you will find this kind of development really complex. And from my experience, this is really not a simple task. And after all, you will end up with your own application protocol, because you would have to define your routing, you would have to define your message format, you would have to define additional headers and metadata, and this is not good. This is somewhat you don't want to maintain all the product evolution, etc. Because at some point in time, someone requests for more features, and you would have to include them and build into your own application protocol, and then it's really hell of maintaining of your own solution. This is not good from my point of view and from my experience. Of course, there is existing solution. Of course, there is something existing like SocksJS and Stomp, which allows you to build messaging over the WebSocket. So this is a protocol built on top of WebSocket. There is Socket.io, and Socket.io is really popular, for example, in JavaScript world. So let's try to build something on top of Socket.io. Yeah, let's try to do that. And let's take a look at Socket.io. Just imagine that we have already built something using Socket.io, and now we have to test this. Now you're in the role of testers. Please enter this link. Please follow. This is really plain link in order to get access to the game. So there is ESGD Socket.io, really plain link. You can put it in your browser and get an access to the game. Please join this assessment, since we have to figure out that Socket.io is good or not good. You're the main kind of people who do final decision. Really plain link, ESGD Socket.io. Now I'm gonna copy this link and gonna enter it, and now I will see, in case I get good network connection, I hope I will. Come on, not at this point in time. If you're using your own 4G, it should be better than mine. Because, yeah, of course, I got the connection, so now I can say, okay, This is my name. So yeah, we can play. Looks that everyone just staying on the map, okay. Just everyone lost the connection. Do you experience the same? Can you play the game? Is it clear? Is it? No? No, it's not, yeah? There is some bugs. Unfortunately, the game itself does not contain bugs, I mean. If I try to rerun and reopen this game, the problem will continue, and the problem isn't in the game, in the business logic. The problem is in Socket.io itself. In Socket.io for Java. This is the evilness part. So if you're going to look at the Socket.io from the development perspective, you will try to build something using Socket.io, we will find the following. There is no integration with Spring. This is the first point of not good development experience, which means that you have to start your Socket.io server in Java and you have to integrate it with Spring Lifecycle like here. That's what you have to do first if you start using Socket.io for Java. Then the API itself is really copy-pasted from Node.js. So the developers just take a look at Socket.io for JavaScript and decided to copy-paste all this JavaScript and put it them into the Java. And if you're going to develop something with Socket.io, you will see the API definition like this. And this is somewhat we are not get used to in normal Java development. In turn, Socket.io is built on top of Netty. From my experience, Netty is really high-performance server, and it should perform really well. That's why I decided to use this Socket.io for Java solution and not others, because of Netty. How many of you heard about Netty or used that? So Netty is really high-performance web server and framework for web development in general, and the main feature is direct access for kind of off-heap memory. So you just got a byte. Those bytes are kind of allocated somewhere on the network card, and instead of copying everything to your heap, you can directly access to those data, to those kind of part of the memory outside of your Java application. This is amazing part of Netty. That's why it's really high performance and doesn't require to involve garbage collector into your development. So far, if you try to build something with Socket.io for Java, you will find that there is no direct access to your byte buffs, and you have to copy everything to your heap. And this is the main reason of low performance in Socket.io for Java. And unfortunately, there is no other solution for Socket.io in Java, I mean like a Java server. That's not good. So there is a point when Socket.io is a pretty good solution, where it works just like a clock. And this point is JavaScript. In JavaScript, it works pretty well. Unfortunately, for Java developers, Socket.io is not the best solution. All right. So it's clear that Socket.io is not good, and WebSocket development for using existing frameworks is a little bit complex, so we have to take a look at somewhat built on top of HTTP2. And one of the most popular solutions built on top of HTTP2 is gRPC. Have you ever heard about gRPC? Okay, a few hands. So gRPC is proper web kind of streaming service or framework built on top of HTTP, and which allows you to create only one connection and stream multiple strings through this one connection. So this is a cool solution. And now we have to assess it and figure out whether it's better than Socket.io or not. So do the same. The link is pretty similar, ESGD reactive gRPC right now. So please use this solution. And now we have to assess whether the performance or gRPC is better. So let me do the same. Let me copy this link. Let me open this link in my browser. Now I have to get access to gRPC version. So let's take a look at gRPC. Yeah, gRPC looks much better. At least everyone is moving on the map. Of course, you have to remember that there is latency. There is some network which caused some latency between my server deployed somewhere in Amazon, one of the data centers at Amazon. So there is some latency, but in general, it looks better. Is it looks better? Is it better than before, than Socket.io? Yeah, it is. It is definitely better. So now we have to get back to our slides, and we have to say why gRPC. First of all, from few point of views, gRPC is built on top of HTTP2, which means that it provides better performance, as we saw. It is in the development because we can, gRPC is built on top of protobuf, and now if you want to build our own API using protobuf, what we have to do, we have to define a few protofiles, which says that this is our definition of our messages, and using the same protobuf, we can define the API for our services. So we can say that, for example, we want to receive plain request response, and we can achieve that by definition of this kind of using this style in protobuf. In turn, we can easily say that we want to achieve some streaming from client to server and from server to client, and we can easily say, okay, I want to stream data from my client to a server, and I want to receive some stream of data from server to client. This is pretty easy. This is one of the main features of protobuf. In turn, there is really seamless integration with protobuf in gRPC. What you have to do, you have to just add your one plugin into your application. You can say, I want to generate my code from this protobuf definition, and this plugin will generate everything for you, and you will get all these files out of the box without almost doing anything. So you would have only to implement your business logic, and that's it. Amazing feature. All right, and finally, there is seamless integration with Spring, so you can say, okay, I want to just say that this is my gRPC service, and it will be get by, it will be understood by Spring Framework, and everything will be wired as it requires, as it's needed. Really simple and good development experience. However, we have to ask the question, of course, because we are engineer, why not gRPC? I guess few of you noticed that there is some lags and there is some latency in the gameplay. Did you experience that during your gameplay? Yeah, there is some latency. So if you're going to Google, and if you're going to look why gRPC is so slow, we will see this, and we will see that, in fact, gRPC Web is fake. This, you can open your browser, kind of this game from your laptop, and you will see the same number of location requests. And if you Google why gRPC is a little bit slow, you will see the following design schema of gRPC Web, which means that gRPC Web is a fake. There is some proxy in between which causes all the problem. First of all, there is Envoy, and since, as I said, browser does not support HTTP2, and from the communication between client and server, nothing has changed in protocol itself, we still have the same request-response communication, which means we have to open one connection, there is no guarantee we achieve HTTP2, and in case of streaming, we have to open a few more connections in order to listen to stream updates over additional proxy, which causes much more higher latency. This is somewhat not good, somewhat that causes lots of problems in communication between browser and server in gRPC. So, of course you can say, but wait, gRPC is pretty reliable since between server and server communication we can achieve only one connection, which should be pretty good. And gRPC developer states that gRPC has back pressure. Have you ever heard about this statement before? A few people. So in general, gRPC developers on every conference says that gRPC has back pressure, and if you're going to look at the API, we will see this kind of definition of subscriber, and we will see that there is this request and method, which allows us to say how many requests we want to achieve from our publisher. But don't fool yourself by this subscriber definition, because if you're going to look at the publisher side, we will see the code like this. This is how publisher can control the data stream on its side. Do you see the problem here? Anyone? Do you see the problem? Let me highlight the problem. Just imagine if isReady field is volatile field, and there is a few thread which is changing or acting on this field. Just imagine that at some point in time, you got access to this isRead field, and isRead was true, so you try to send the next element, but when you try to send this element, someone changed this field to false. And now there is a chance that you oversent a few more elements. So, to summarize, if you're going to Google for this problem, if you're going to Google for back pressure control in gRPC, you will, at some point in time, you will find this issue on GitHub. And the most important that the general back pressure problem were kind of popped up in 2016. But anyways, a few weeks ago, I found this question from a real person on GitHub who complains about this grazing condition. So, and official maintainer of gRPC says that, yeah, the racing is absolutely possible. And there is no chance to prevent that, unfortunately. Yeah, so obviously, there will be some racing. And the only guarantee that we can get from gRPC, if you read is read field and it returns false, there is no guarantee that your application that uses gRPC observed it yet. Curtis. This is a problem. So to summarize, it's clear that publisher can oversend a few more elements to the memory using gRPC. But just imagine, what if we have a few more publishers in our one simple Java application, which can overproduce a few more elements to the memory? So what could happen? Your ideas. In order to understand what could happen, we have to run a stress test. Of course, we have to assess it. We have to consider, for example, our pipeline, because this is an important part of our ecosystem. So let's focus on this part, and let's test what happens if, for example, we run a stream of data under some specific circumstance. So in order to simplify our example, we are going to remove Kafka from this, because we have to emulate Kafka and run in Kafka and fill in Kafka with some data. It's another challenge, so let's try to avoid them. And let's consider only kind of limited number of services in our pipeline. So in order to emulate Kafka, we are going to use a convenient way from Project Reactor. So we are going to use a client which will generate data only when there is a demand from our subscriber. So one subscriber said, I'm ready to receive a few elements, this guy will produce a few elements, the exact number of requested elements. Is it clear? So far, so good? OK. So now, what we have to test, since the distributed system is unstable and we can get fast subscriber or fast kind of subscriber at the first point in time, so everything should be fine when there is we have stability in the system. We have to test what happens when our subscriber suddenly became slow one. And we have to figure out whether all the part of our pipeline will survive or die during this test. That's what we are going to check during this scenario testing. In turn, in order to make our test more kind of closest to what we have in real cloud, because today we are running Kubernetes, we run our application in containers, and we are given only a few gigs of memory, only a few gigs of RAM and CPU, a few CPUs to our container. So we have to check and we have to make our test as close as possible to what we are running in real cloud. So if you are going to run this test, there is a link to real video. You can watch the video and see the same, and kind of look at the same test. Once we start sending data and make our subscriber really fast, we will see that everything works fine. But once our subscriber became slow, we will observe that for some period of time, our publisher will produce with the same speed. Of course, it will slow down a little bit after some point in time, but anyways. If you're going onto measurements after the whole test, we will see the following. This is on top, you can see the throughput. Can you see that? Yeah, there is a throughput of publisher. So the top graph is the throughput or measurement of the throughput of publisher. On the bottom side, the throughput of subscriber. So if you're going to measure or merge both graphs, we will see that there is kind of a point at which we start experiencing back pressure. Yeah, it's a little bit unclear what's going on my screen. And I unfortunately can't do it a little bit lighter, I say. But anyways, there is two curves here, and top one is publisher throughput. The bottom one is subscriber one. And as you can see, there is some gap. There is some over throughput by our publisher. So if you're going to ask a question where all those data are stolen, are kind of stored, you will see that they are stored in the memory. And the next point in time, you will see that you got out of memory, and this is somewhat we don't expect from real production and from our servers in real production. So, in general, to summarize back pressure in gRPC, there is some back pressure, but this back pressure implemented only on the level of HTTP2. And if you want to achieve the whole back pressure during all the pipeline, we have to use a little bit different solution because gRPC can't provide us with that. And you can believe me, because I spent lots of time to make gRPC really reliable. I spent a few nights and weeks in order to provide proper reactive wrapper on top of gRPC, and I failed. Unfortunately, I wasn't able to achieve proper backpressure control with gRPC, even with reactive streams specification. So, to summarize what we got so far, everything is either slow, like HTTP, hard to implement, or lacks support in the browser, like with gRPC. In some cases, flow control is not far from what we need, so we have to find a little bit different solution, or we have to create a workarounds for that. But do we want to spend our time? Do we want to spend our money implementing all this and solving all this problem? The same question were asked 4 years ago at Netflix. Because Netflix, as you heard, this is a real shop of streaming data from one side to another, and in their cases, they got only almost the same kind of data streaming pipe. In their cases, they got reliable servers on their side, but they have to stream lots of data to their clients. And they can't control all the clients. They can't scale your mobile phone, and they can't prevent that your phone started working slowly or faster at this point in time. And they tried gRPC to put everything, like to replace all plain HTTP communication, because they believe that gRPC provides proper backpressure, as Google state, and they failed. You can read about the use case and the studies on usage of gRPC from one of the ex-developers in Edge platform at Netflix, who explains why gRPC failed and just crashed the whole ecosystem in a second because of this type of communication in their system. So they start thinking, we need real backpressure. We need real control of backpressure along the whole pipe between few chain, not only between server and server, but between whole kind of pipeline of communication. And since were invented RxJava, they invented lots of amazing things for distributed system, they decided to create a real reactive streams protocol with real backpressure. And that they named this protocol RSocket. So you may wonder, what is RSocket? From my point of view, RSocket is a bright future, because RSocket is exactly reactive stream specification as a network protocol, with all this future and all this backpressure propagation as a packet over the network. This is an important point. So why RSocket is fast and good enough for our development? First of all, it's a binary protocol. If you want to send one message from one client to another, you have to take care to decode it to binary format, but RSocket will take care to deliver this whole message as one frame, so you will be able, on the other side, on the recipient side, to just take this packet and decode it back without any problem to the same message. So RSocket takes care about message delivery in binary format. In turn, it multiplex protocol. So now, if you want to send lots of logical streams, RSocket will take care about kind of delivering all of them in one connection, in one whatever type of connection, marking them with some logical streaming, so the recipient side will be able to decode it back and to map to particular recipient streams. This is good part of RSocket. In turn, what you have to use, for example, with RSocket Java is just plain reactive streams. You can use Project Reactor or RxJava, and this is pretty cool. What else? This is transport agnostic. This solved the problem of gRPC because gRPC is pretty tight coupled with HTTP2, and there is no other chance to use gRPC over other protocols. That's why we can't simply use gRPC between between browser and server. With RSocket, you can use whatever you want. You can use TCP because this is just application protocol. You can use WebSocket between browser and server. You can use HTTP2 if you want. There is support for HTTP2 as well. You can use Quick. You can use Aaron if you want. And Aaron is rated UDP. So you can use the same protocol, the same API, the same behavior, and kind of the same type of communication over any transport, because protocols, this is just a protocol, and there is no tight coupling with particular transport. What else? This is bidirectional protocol. It allows you to send messages back and forth, which is pretty cool. So once you created a connection, there is peer and peer, and both of them could implement message handling, and this is pretty amazing because you now don't have to ask client to send your data, to send the data or send some stream of data. The server can in advance send something to you. What else? There is backpressure support. There is real backpressure support because now, once you send or say request something in real Java method, This call will be transformed to real packet, delivered to recipient side, decoded back to the same Java invocation, will be invoked on the publisher side, so publisher will be able to send exactly the same number of requested messages. What else? RSocket is not only about streaming. RSocket allows you to send and interact with your client and server in any kind of interaction. So there is request-response, plain request-response communication. There is fire and forget, or kind of advanced request-response, when you can send data and forget, release your resources as fast as possible. There is request stream, so you can request a stream of data and listen, for example, for updates from the server side. Or you can send stream from the client side to server. You can stream kind of data from client to server, and this is an amazing part of RSocket. What else? What other notable feature here? There is listen, so it allows you to avoid circuit breaker because now server can manage the number of requests between all connections. This is an amazing feature of RSocket. There is resumability. Just imagine that you're building mobile server communication and your mobile just switching, for example, switch it from Wi-Fi to the net to the normal 4G or 3G network. So it basically means that you can lose your connection, or WebSocket or TCP connection, which means that you will lose all streamed data. RSocket has a built-in feature in the protocol which allows you to send your previous session and continue all streams without losing anything. This is a cool feature of RSocket. And there is fragmentation. Just imagine that you are sending really huge PDF files or whatever files. RSocket allows you to fragment all the data into smaller chunks and then deliver them asynchronously one by one without losing anything. So, if you're going to look at the whole RSocket ecosystem, you will see that there is support in any different languages. It allows you to build any kind of API using any kind of message format, and the most important, run on top of any kind of lower network protocols. So let's try to assess RSocket and figure out whether RSocket is better or not. So let's do that. The link is absolutely the same. So let me just open this guy and see whether it's better or not. So here we go. And it looks much smoother. Of course, there is some network latency, but let me play a little bit. Is it better than before? Any response, guys? Is it better? No? Yes? Your final decision. Yeah, it's better. Of course, I have some network latency because of unreliable Wi-Fi in my room, but anyways, if I try to run this on my phone or phone network, it should be better. So let's go back and let's figure out why it's better. First of all, if you try to build RSocket server using Java, what you have to do is just simply define RSocket, say that I want to receive some data, define your socket handler or connection handler, say which kind of transport can I use. This is absolutely transparent that you can change transport without losing your business logic and without rewriting anything. This is cool. So you can just use WebSocket or TCP without changing anything. Then you can say start. Since everything is asynchronous and built on top of Project Reactor, you would have to wait for startup, and then you would have to block, for example, if it's just plain public static void main, you would have to block the main thread in order to keep your application running. What else? For example, to handle connection, to respond to your request, you can create RSocket. RSocket is the main kind of interface in our RSocket library. This is obvious. And for example, you can override one of the available methods, and you can send and respond with reactive streams to some request. This is pretty cool, using Project Reactor. The main data type in RSocket is payload, so it's a binary representation of your payload, and you can encode whatever you want. There is byte buffer payload. This is taken from Netty, which means you can do direct access to your memory and create zero-copy kind of message sending in your application. What else? The whole Java application could look like this, but moreover, you can build almost the same, for example, client on the JavaScript side with the same API without changing anything, almost anything. And you can define MIPE times, keep alive, etc., and so forth and so on. And you can choose in the same way transport on on top of which you want to send all these reactive streams. So you can use RSocket in this way, but sometimes we need to have a real API, for example, like in gRPC. If you're a gRPC user, you can use the same definition of the API because RSocket provides integration with protobuf and provides the same RPC API integration as gRPC does it. So now what you have to do, you have to define the same plugin, you have to bring few dependencies, and that's it. You will get the same generated files as with gRPC. What else? If you want to use, for example, integration with Spring, there is RSocket in Spring messaging. This is a real cool feature. What you have to do, you have to just bring one starter, and you will get RSocket in Spring. And now what you have to do, you have to just define only a few configurations, and then you can say, okay, I want to define my controller in absolutely the same way as before with REST controller, and you will be able to do that because there is the same annotations, and now your reactive streams will be mapped back to RSocket and Force. This is a cool feature, and in general development with RSocket in whole ecosystem, because there is support in Spring, there is support in RPC communication, will be super amazing and cool and smooth. That's why I love RSocket. So what about stress test? If you're going to run some stress test, we will see the following. The case is the same. We are sending data. We have the really fast subscriber, first of all, which means that subscriber has to request some data in order to get the response. This is reactive streams, real reactive streams. So once the publisher got real request, it will start sending data. So your subscriber will asynchronously request data, but of course, at some point in time, it could become slower. It would have to take a time to process everything. But now, if I have to take time to process my data, I won't request anything. So I can take my time, and once I'm ready to request more, and I know that I'm slow right now, I will request less data or make smaller request. And it will make my stream smaller, or slower, I mean. If you're going to look at the throughput of RSocket publisher and RSocket subscriber, again, it's not well defined, recognizable here, and we will try to merge both those graphs. Both of those graphs, we will see that the curve is absolutely identical. It matches to the throughput of subscriber and publisher. All right, so to summarize the main advantages of RSocket. First of all, simplicity in development, integration with Spring and with RPC and like gRPC and protobuf. Efficient resource usage, one connection. High performance because binary data sending. High flexibility because you can do request response, request streaming, and all kind of normal communication in your applications. And there is really effective reliability because you have real backpressure propagation through the whole of pipeline. Since we are engineers, we have to listen to disadvantages as well. And the main disadvantage of RSocket for now is that this framework is still under development. RSocket protocol itself is still in the phase of 0.0.1, but it doesn't mean that it's not production ready. It just means that there is not all the feature implemented in the protocol and in the particular implementation for particular language. In turn, the next disadvantage is that community is still a little bit narrow. So we don't have really wide adoption of RSocket, but I'm working on that. I'm planning that at least a few people or a few more will try RSocket and read about RSocket solution today. So I have to say that maintainers that do their best to improve RSocket, to implement RSocket in their infrastructure are pretty good. If you're using Facebook, you're using RSocket today with GraphQL because Facebook decided to move from HTTP to RSocket in order to kind of decrease number of spans on their infrastructure, and they got success. Our company and Pivotal are doing their best to make this framework integration as much as seamless as possible, so you can use it with Spring, with RPC communication, and you won't experience any bugs. And Alibaba saw all this progress from Facebook, from our company, decided to start adopting RSocket in their cloud infrastructure as well. And this is super amazing. So, to summarize all the features of RSocket, we have to look at this table. Every protocol has its own benefits, of course, some disadvantages and advantages like adoption and community. But yeah, as I said, each protocol has its benefits. Socket.io works pretty well in JavaScript world. gRPC performs really well in some certain particular cases, but if you want to build real reactive system which is reliable, you have to use proper solution like RSocket. So, If you want to learn a little bit more about RSocket, please follow me or my company on Twitter. I'm usually tweeting lots of things about RSocket. If you want to watch more videos and if you want to ask more questions about RSocket, there is a community chat, so please join it and ask whatever you want. There is a video channel, and there is integration with Spring. So if you want to start using RSocket with Spring, please take a look at this link. Finally, if you want to get real enterprise version RSocket with routing, with distributed cluster of RSocket, there is a proper solution as well, on which we are working today. So I don't have enough time for questions. It's a time for lunch. So please enjoy the rest of the conference. Please enjoy your lunchtime, and thank you for your attention. If you got any questions, I'm still there.